Okay everybody, welcome to Unit 10. Here's a supplement video if you need it for whatever reason. You're absent or you just need it for extra support, totally fine. Unit 10 is all about inverses and logarithmic functions. This first section, 10.1, what this video is about, is solely about inverses. We're going to talk about what that means, but I think it's just better if we kind of dive right in and just go along as we see. So example 1 here. Graph the reflection of the point 4,5 across the x-axis, the y-axis, and the line y equals x. Write the coordinate of the new transport point in each case. Okay. So, for this, for my situation, I've got my phone here. I'm doing it all on my phone. You can see I've got it on airplane mode, right? All that jazz. I am using a stylus, so I'm not going to redraw this graph 3 times. You're welcome to do that, but I'm going to put everything just in this middle graph right here. Draw myself some axes. The point 4,5 occurs 1, 2, 3, 4, up 1, 2, 3, 4, 5. Right there. So that's our original. We'll even label it, call it A. That's our original point. Fabulous. We're going to transform this function 3 different ways. What 3 different ways? They want us to go across the x-axis, reflect across the y-axis, and then reflect across the line y equals x. Now I know that sounds super complicated. It's not a format we usually see, but it's really not that hard a line. It's just the diagonal that goes up the right side of the graph. It's where 1 equals 1, 2 equals 2, 3 equals 3, so on and so forth, right? So it just creates the diagonal across the first quadrant. Okay, but let's start with the x-axis, because that's not super hard. Where'd my graph go? The x-axis, that's this horizontal one here, right? So instead of being out 4 and up 5, it's going to flip over that, and it's actually going to be out 4 and down 5. So we're going to out 4, down 1, 2, 3, 4, 5. There we are. We'll call this A prime, or maybe you don't remember that notation. We'll call it B. So B is going to be our reflection over the x-axis. Over here on the side here, I'm going to make some notes. Once again, if you're using this, that's fine, but or if you're using all 3, that's fine, but you definitely want to take notes on somewhere. I just want to make it thinner. There we go. Okay. So our original, that was the point 4,5. Right? This new point, point B, well, what are we looking at here? What happened to it? So B that was the x-axis, right? That's where we flipped over the x-axis. What did we do? Well, we just said it's still out 4, right? But now it's down 5. It's out 4 and down 5. So this is the point 4 comma negative 5. That's interesting how that happened. So the x stayed the same, but the y changed. We flipped over the x-axis and it changed the y. That's interesting. Let's try the y-axis now. Let's see what happens with the y-axis. Let's do green. Alright, so the y-axis, remember we're starting back at this original point here. We're going to flip over that way, right? Reflection, you think reflect in the mirror. It's the flip of you around. I don't know, girls, if you've ever tried to do your bangs in the mirror, right? You have to work backwards. It's really annoying. So hopefully that wasn't too bad for you. But we're going to do the same thing here. We're going to flip it over the y-axis. Well, it's 4 out to begin with, so it's going to be 4 back. 1, 2, 3, 4. But it's still going to be 5 up, and we'll call that C. Or maybe A double prime if you want. Okay, so C was the reflection over the y-axis. The y-axis. Well, what happened to that point? Let's see. Like we said, it's still 5 up, but now it's back 4. So instead of going 4, we went negative 4, but we stayed positive 5, right? We stayed positive 5. That's also interesting how when you flip over the y-axis, the y stays the same. The x is in fact the one that changes. That's interesting. All right, last one. The line equals, I can't talk right now. The line y equals x. That's what we need to flip over, but it's not on the page yet. So let's go ahead and draw that. Remember, it's like I said, it's not the most complicated line. It may look like it. Most of us prefer the y equals mx plus b form. You're welcome to add a 0 at the end and highlight that the slope is 1. That's fine. But this line's really, like I said, just the one where places where 1 equals 1, 2 equals 2, 3 equals 3, 4 equals 4, so on and so forth. So look, this red line here. That's what we're flipping over. Okay? Now, obviously, I didn't draw my axes right across the middle, but that doesn't really matter, right? Just want to make sure, follow that line all the way down. Okay, so this is the line y equals x. You can see it cuts it in half, right? Goes through the origin, 0 equals 0. And we want to flip over that. So we go back to A. You might be thinking, well, this one's not up or down, right? This one, I don't know whether the x is going to change or the y is going to change. But it's okay. We can just do this visually. When we flip over, it's just going to flip to the other side of that box, right? It's going to flip to right here. We'll call it D. Any guesses about what this is going to be, where this is going to be? There could be, you know, let's switch to negative, negative. It could do something with just the x, something with just the y. Let's count it and see. So we originally had what? 5, 4. Now we are going out 1, 2, 3, 4, 5, and up 1, 2, 3, 4. Check that out. This is now 5, 4. So D, our D value, flipped over the line y equals x, that changed to 5, 4. So it didn't become negative, right? They weren't both negative. That's just a rotation of 180. But this ended up being backwards. We switched x and y. And this one is the most important, to be honest, when it comes to inverses. Because switching x and y, that's kind of the theme throughout the entire section here. Okay? All right, cool. Now, as I was saying, this line is most important. We can do this with more than just points. If you just put 2 points together, like, I don't know, let me just draw another point up here, right? And then let me go ahead and connect the dots, right? I could also flip this one over. I could flip it over here, and then I could also connect the dots, and I get sort of this mirror image over x and y. These two line segments are called inverses. This line, y equals x, is the most important when it comes to inverses. While flipping over the x-axis, the y-axis, that's kind of unique and fun, and you know, it can make pretty shapes and things like that. This one is actually where you get inverse functions from. So if you look at another example, down here we see a more complex thing. You still see that green line, y equals x. It's just the diagonal across the page, nothing different, super straightforward. And then you've got this weird function f of x, right? This it's cubic. We can see that because it's kind of an S shape, right? It's got a little bend in it, and that's what happens when you have a cubic function. When you flip it over that line, you get g. It kind of looks like a little vase or a fish or whatever you want to call it. But that's basically what's happened here, is you flip it over, y equals x, and you get g. And so these two functions are inverses. F is an inverse of g, g is an inverse of x, right? If we were to take g and flip it back, you would also get f, right? So they're inverses of each other. All right, now, we're going to be solving for these. In this class, though, this is college algebra prep, right? College prep is prepping for the class college algebra. So we're going to focus mainly on the algebra behind these, how to find them algebraically. But the graph is still very important. The graph is probably the easiest way to really figure out what this means. What are you finding? What are you doing? So let's start with this example down here, example number 1. And I'm going to show you just how easy it is to find these algebraically. Now there's a few things you may have to think about, like domain and range, but finding these is so easy. It's so easy, straightforward math. You just have to switch some stuff. But let's start with example 1 so we can really kind of go with this graph idea for a while. Example 1, graph the line y equals x. Okay, that sounds like it's going to be important. F of x equals 3x and g of x equals 1/3 x on the graph provided. Are f of x and g of x inverses? If so, prove it algebraically. Okay, so they don't even want us to do it algebraically first. They want us to start by doing it geometrically. They want us to graph it, right? They want us to put it on the graph and see if they are inverses of each other. Well, to do that, we have to start with this line y equals x. So let's just start with that. Let's draw some axes. And some axes there. Cool, okay. Maybe they're perfectly in the middle, maybe they're not. I don't know, they look pretty symmetric to me. Alright, the line y equals x, that goes up, right? Just goes. Now I'm going to make this one a little more accurate, right? I'm going to put dots everywhere and connect them. That way I can really see if these two things we're about to draw are inverses of each other. My mind always plays tricks on me going backwards. Okay. And no, yep, that's good. Okay, and then that one, that one, that one. And notice I didn't, oh, I did. I didn't quite hit the side on that one, but I did on the other one, so it actually is the middle. There just must be an odd number of spaces, and that's okay. I don't really care about the part. Alright, so I graphed y equals x. Now I'm going to graph f of x equals 3x. Now recall way back when that function notation isn't anything super special, right? It just means that x is the variable, x is the argument, and it is a function. This passes the vertical line test. If I put in 1x, I'm only going to get out 1y, right? If I put in 2, I'm not all of a sudden going to end up with 5 different answers. 3 times 2 is 6. That's it, right? Just the 1-to-1 ratio. 1 in, 1 out. So don't panic when you see something like this. Remember, you can just easily change it to y. Totally fine. It also just helps if you have multiple lines you need to graph, right? The first one is f of x, the second one's g of x, instead of both of them being y and being incredibly confusing, right? So that's just an easy syntax, no reason to panic. Okay, I could either make a table, or I could just throw on a +0, right? Now I can graph it, so start at 0, and then the slope goes up 3/1. And I want to be, again, a little more accurate and less sketchy than I have been in other graphs. It sounds a little strange, sketchy, but instead of a rough sketch, I'm really kind of plotting a lot of these points because I do want to see if these actually match up, right? I want to see if these are in fact inverses. Okay, there's the top half, and then I'll go back 3, down 1, oops, back 3, down 1, back 3, down 1, back 3, down 1, and then I'm going to go off the screen a little bit, back 3, down 1, or off the graph paper. And then I will connect the dots. Okay, so there's a very accurate 3x, right? Y equals 3x. That's the slope of 3 going through the origin. All right, now let's take a look at the other line, or the third line they want us to graph, right? Because technically the y equals x is the first. The third line is g of x equals 1/3 x. All right, but again, the g of x can be replaced with y. And this is virtually the same thing. It just has a slope of 1/3, not 3/1. So this is going to be, again, starting at 0. But now instead of up 3/1, it's going to be rise over run. So rise 1 and out 3, right? So it's going to be a 1/3 slope. So let's actually just draw the dot there. And then we're going to go up 1, out 3, up 1, out 3. Up 1, out 3, and then it looks like my last one would be like over there. And then we will connect these for a super accurate straight line. Cool. And then we'll also do the back side, right? Because we can't just have one side of the graph, gotta have both. So down 1, back 3. Down 1, back 3. Down 1, back 3. Down 1, back 3. Erase this random green mark that was there. And then it looks like I go off the graph a little bit. And this one would be a little closer. Okay. So now we're going to connect those ones. And we're good. Okay. So I have my two lines now. I've graphed all three as they say. And now they ask the question, are f of x and g of x inverses? Well, what would make them inverses, right? They have to be reflections of each other over that diagonal line y equals x for them to truly be inverses. Well, they definitely look like it, right? If you take the red line and in quadrant 1 you flip it over to the bottom, you'd get the purple line. And then if you took the bottom half and you'd flip it up to get the purple line, right? It kind of looks like someone just took it and went whoosh, all the way over. And then and even the same back, right? It looks like someone took the purple one and flipped it back to red. Could very well be the case. So I'm going to lean towards yes. I think this looks pretty similar. I think these look definitely like they could be reflections of each other over the line y equals x. However, they say if they are, prove it algebraically. So how are we going to prove these algebraically? Well, to prove it algebraically or to find an inverse, this process is the same. All we're going to do is switch one. We're going to switch the places of x and y in one of them. Why don't we go with f of x, because I know you guys prefer whole numbers to fractions, even though it really doesn't make a difference. But we're going to write f of x. Okay, so let me get a different color. So, geez. Okay, so here we have f of x equals 3x. Now, if it makes your life easier, you want to write y instead, it's highly recommended. I always write y, even if it's a function, because I don't like having multiple parentheses. Sometimes there's stuff that's going to have parentheses already in it, and I don't want to replace it with something that has another parentheses. So I just like to switch it to y. Totally fine. Totally fine. And now I'm going to make the switch. So I've switched it to, or I've rewritten f of x as y. Now I'm going to swap out every x and y. So every y becomes x, and every x becomes y. Okay, so it's going to change like that. I'm just going to change them. In this example, it's really easy, right? We can just see that instead of y equals 3x, we have x equals 3y. Awesome. So that's the first step. The next step is we got to solve for y, because we like our equations to say y equals, right? Not x equals. We like y equals. So let's go ahead and maneuver this for y. To get rid of times 3, we just divide by 3. And we get y equals, and we'll keep it the same, x over 3 equals y, otherwise known as y equals 1/3 x. Well, that sounds awfully familiar. That was, in fact, g of x. Okay, so the inverse of f of x is going to be y equals 1/3 x, and that was the function g of x. So we've now proven it algebraically that these two are really inverses of each other. We didn't have to go point by point and prove that every single point went over the line. All we had to do was switch x and y and solve for y. So it's not that hard. That's the big idea here. That's the biggest idea you can go with. The linears will always be inverses of each other, right? Because you can't flip a straight line over a line and all of a sudden end up with a curve, right? It's going to stay a straight line. So linears will always be inverses of each other. That's super simple. However, if we look back here at our more, curvy example, right? It's the f of x is a cubic, right? When you flip it over, it's not really a cubic anymore. It's almost not even a function, and that could be a problem sometimes. If you were to draw a vertical line, write it too, it may not even pass. It might not even be a function. So it could be the case that you don't end up with one-to-one, which, okay, that's fine. For the purposes of this class, we're more focusing, like I said, on the algebra, on the fact that when you switch it, you get the inverse equation, if you want to call it. But yeah, so often you're not going to end up with the same function, especially with something like cubic or quadratic or rational or radical or any of the higher up functions we've definitely done this year. And more often than not, you're going to end up with something something very different. Let's try example 2, and maybe you'll see what I'm talking about. Example number 2, find the inverse g of x of the function f of x equals 4x squared and determine its domain value over which it exists. Okay, we'll talk about that in a sec. Let's just start with the function part. Function f of x equals 4x squared. Okay, in order to solve this, I'm just going to change that to y because my life will be so much easier. So here was my original, right? Y equals 4x squared. Now I'm going to swap out. So I'm going to swap the x's for the y's. I'm going to swap the y's for the x's. Awesome. So y equals 4x squared becomes x equals 4y squared. That's not super hard, right? I can rewrite letters. It's not a big deal. Just rewrite the letters. Now I'm going to solve for y. Solve for y. I know it's tempting when you have a 4 there that's a perfect square. Everybody likes to take the square root first. I wouldn't do that. I would divide by 4. Divide by 4. Right? And then you get x over 4 equals y squared, right? And now you can take the square root. We get y squared. How do you undo a square that's all by itself? You square root it, right? Square root, square root. Can't forget that plus or minus. So we end up with y equals plus or minus square root of x over 4. Little bit of simplification we've seen in the last couple chapters, right? If you have a perfect square root on the bottom, square root of x over 2. So technically you could have done the square root first, you would have ended up with the same answer. That's really up to you. But see, I like to go reverse PEMDAS no matter what. I like to deal with squares last. Square roots are ugly. I don't like to deal with them, so I do them last. Questions? I hope there aren't any. If there are, you can send it to my email or come see me. Okay, cool. Now the second part. Domain value over which it exists. What does that mean? Domain value is something we have to worry about now, right? I can plug anything I want into x squared. The original function was not a problem. Can I get anything out of an x, right, under that radical? The radical here is the problem. When I have an x there under the radical, sometimes things aren't going to exist. We've talked about this in chapter 8, right? You can get complex numbers. What numbers would do those? That would be negatives. Negatives would give you things that are complex, and we don't want complex here. We want, you know, stuff we can draw on the graph. Complex numbers can't be drawn on the graph without a special kind of graph. So this would not work. We'd have to find out what values would give us bad outputs. What would make y not work? And in this case, x would be negative, and negative wouldn't work. So in this case, the domain is x is greater than 0. There's only going to be a real function for where x is greater than 0. And if you're not convinced about that, I dare you to try it. Try plugging in a number there that's a negative number to x and tell me that you can get a real y out of that. You can't, right? You can't do that. You can't get a y that's real out of y. It's not that you can't get a y. You could definitely get something like 6i, but we don't want that. We can't graph that. So the domain is x is greater than 0. Cool, that wasn't too hard, right? Just had to think about it. All right, let's try another one. Find the inverse f inverse of x. That's just what this notation means here. Though it's very much like chapter 4, right, when we had a inverse. Doesn't mean f of x. It doesn't mean f of x is now being raised to the -1 power or anything like that. Okay, it's just a notation. If you want to change it to g of x for a sec, go for it. Right? In fact, really, in the last problem, we should say g of x is equal to plus or minus the square root of x over 2. But yeah, it's just a notation. It's just a notation. For the function f of x equals x times x minus 1, and determine the domain range values over which the inverse exists. So once again, they are not asking about the original function. They only care about the domain and range of the inverse function, if it in fact exists. So our original function, I'm going to rewrite as y equals x plus 1, or x minus 1, pardon me. Yeah. Instead of f of x, because I want to do that switch thing, right? So I'm going to change it to y for the time being. Just can't remember, again, to change it back. Now I will switch out. Every y becomes x, and every x becomes y. Notice I said every x becomes y. In this function, there are 2 x's. Now they both become y. Okay, so you don't just switch out one, you're not swapping sides, you're changing every occurrence of y becomes x and every occurrence of x becomes y, okay? So you're switching letters, you're not switching places. Okay, cool. Alright, now we gotta solve this for y. Well, there's unfortunately two spots where y is, right? So let's get rid of the parentheses here. We have y squared minus y. Some of you may argue that why would you do that? Why wouldn't you just move it to the other side so that you could solve for y? If I put 2 y's, if I put one on each side, there's actually no way that I would be able to separate them into one y, unfortunately. It's too convoluted right now. So by doing this, I can start approaching that quadratic formula, right? Okay, so we have distributed it out. I'm going to use the quadratic formula. The quadratic formula is going to be the only way I can solve this. However, I can only use the quadratic formula if it's equal to what? That's right, if it's equal to 0. I can't use that yet because it's not equal to 0. Yes, it's equal to x, and x could be 0, but it doesn't have to be 0 yet. So what I'm going to do is a little cheater move. I'm going to move x over. That's not really even a cheater move. We did that so many times in all of our other chapters where we just move things over, right? We move the 8 over or the 6 over, right? And it always just goes on the end as c. I'm just doing it with x. X is just a letter or just a number I don't know yet, right? It's just a variable, and a variable is just a number I don't know. So I'm just going to move it to the other side. And now I'm ready to use the quadratic formula. So it looks like my numbers here are 1, -1, and yes, negative x is my number. This is something we haven't done before. We haven't plugged in variables, or maybe we've done it once, but not often. We haven't plugged in variables to the quadratic formula, right? So we're going to do it now. y is equal to, right, because that's the squared one, y is the one I want, right, so I want to make sure I put y outside. X is equal to, y is equal to minus b plus or minus the square root of b squared minus 4a, and then c is negative x, and that's where my variable is going to go, all over 2a. Cool. Alright, that wasn't anything different. I just plugged in a, b, and c to the quadratic formula. Little simplification now. You get 1 plus or minus 1 minus, oh actually this would be negative 4 times 1 is negative 4 times negative x would be plus 4x all over 2. And that would be my function. Okay, and I'm even going to change y to what they wanted me to call it. The inverse function, right? So now that I'm done, I can just change this to f inverse of x is equal to 1 plus or minus square root of 1 plus 4x over 2. You might be thinking to yourself, Miss K, how can you be done with that? That thing is ugly. That is ugly. There's no way that's the final answer. If you can find some way to simplify that, go for it. But honestly, there is not much you can do without making it more ugly. So I would say just leave it there. Leave it there. It's okay. These things might not be pretty. Are they difficult to find? Not really. You just switch x and y and you do a little maneuvering. Are they pretty? Most often not. You can get some pretty crazy looking inverses, but that's okay. Nobody cares. You just care that you switched x and y and you solved it. You found the inverse. You simplified it as much as you could. The other thing you have to do is consider the domain and range. Well, the domain here has kind of the same problem as the last one, right? We're okay with 1, there's no x there. We're okay with the 2 on the bottom, there's no x there. Nothing could fall apart there. It's really under the radical. We've got a variable there under the radical. If that somehow drops to a negative, we're in the same problem boat as we were last time. We can't have real answer if there's a negative under the radical. So what would do that? Well, in this case, it's not just x, right? This whole expression can't be 0. So we're going to have to say is greater than or equal to 0. You could just solve equal to 0 if that makes you feel better. Just don't forget the greater than part later. But let's solve this. So subtract 1, you get 4x is greater than or equal to negative 1. Divide by 4, and you get x is greater than or equal to 1/4. So for here, the domain, x has to be greater than or equal to negative 1/4. If it's not, then it's going to be negative under the radical, right? X can't be 0, or x can be 0. If x is 0, then that whole expression turns to 1. That's fine. But if x is greater than, or x is less than negative 1/4, all of a sudden you're going to have a negative, right? So we don't want to do that. We want to make sure it's positive. So that's our domain. In your homework, they may ask you to write it as an interval. Remember, if you want greater than strictly, you would use parentheses, but I don't want that. I want greater than or equal to. So I go like this and say negative 1/4 from negative 1/4, including that, to infinity. That's okay. And then infinity always gets a parentheses, right? Including negative 1/4 all the way, comma, to infinity is my domain. Once again, your homework will ask about that. Some upper level classes may ask about that. The calculus route, if you're going into engineering or anything with science, you're probably going to have to draw an interval, so they are pretty important. If you're going with something into like interior design or something like that, then usually the inequality notation, this one right here, is used a lot more. So for this class, I don't really care. It's totally up to you, but you know, they are important to know both ways. Alright, now range. You might be thinking, Miss K, I can't do this twice. Range is so much easier. Once you've found what x can't be, you've kind of found what y can't be. You just got to plug it in. Okay? So just take this and plug it in. If I plug that into here, that's going to be 0. Right? Because I just solved that for 0. Right? So if I plug it in there, I'm going to get 0. And so y would have to be greater than or equal to 1 plus or minus square root of 0 over 2. Well, can you see what's going to happen there? The square root of 0 is 0. plus or minus 0 is not going to do anything. So that's just 1/2. So the range, y has to be greater than or equal to 1/2. It's only going to be greater than or equal to 1/2. It's not that it has to be, it's that it's not going to be anything but greater than or equal to 1/2. As an interval, once again, that's including 1/2 all the way to infinity. So we're not going to hit 0 with this inverse. We're not going to hit -5. We're just going to go at least out -1/4 and then at least up 1/2. That's where it's kind of going to start. Or that's where the bottom vertex might be, right? Alrighty, that's how to solve that one for its inverse. This is actually the final answer, and then your domain and range are over here. Cool, let's do another one. Find the inverse, f inverse of x, of the function, oops, little typo there, pardon me, f of x equals 3x squared minus 5, not times it, and determine its domain and range values over which the inverse exists. Okay, so we have y equals 3x squared minus 5. Once again, I'm just rewriting it as y for clarity's sake, right? I don't like multiple parentheses. And then we switch. We have x equals 3y squared minus 5. I hope that part's not too hard, right? If it is, then you should come see me so that I can help you out. But that's the majority of how to find an inverse. You guys got to switch. After that, it's everything from 6, 7, 8, right? Just working with quadratics and sometimes radicals, and sometimes later on we'll see rationals. But that's majority of how to find it. Once you've switched it like that, you have the inverse. It's just not in a format we like. All right, so let's go ahead and solve this then for y. We'll start as far away from variables as we can, add 5 to both sides. Now, something I see a lot is people forget that x is on the other side now. They assume it's not there. They just say, oh yeah, okay, so 5 is equal to 3y squared. And then they keep going and they solve for y. But that's not the case. This is a whole equation. The x is still there, okay? So don't forget that. It's x plus 5 now is equal to 3y squared, not just 5. Okay, so that could be a big source of error that I see happen a lot. I even myself fell into that trap a couple times, and I'm not proud to admit it. But I fixed it now, as you should too. Okay, next we'll divide by 3. And we get x plus 5 over 3 equals y squared. Notice how the left-hand side is now getting bigger and bigger, and it's not coming down to a very pretty number. That doesn't matter. There's a reason that every single section we've done in this class has had what we call a literal equations section. It's because that's what we've been prepping for. We've been prepping for this. The fact that our equations, after we take the square root, are going to look crazy on the other side. They're going to look like y equals plus or minus x plus square root of x plus 5 over 3, right? Do we care? No. Do we care that it just suddenly went all the way to a crazy radical? No, we don't, right? Because that's just the inverse of the function. That's what it is. If we plug it in, that's what it's going to look like when you flip it over the line, y equals x, okay? This one doesn't simplify like the last one did, or like the 2 times ago did, because there is a 3 on the bottom. But we didn't have to use the quadratic formula because there was no middle term, right? If there was an additional y, if this was 3y squared plus y minus 5, then we would have to use the quadratic formula. We didn't have to do that here. If you wanted to, you're more than welcome to. It would end up looking like this, regardless. You'd have no b term, b would be 0, all over 2a, and you'd get the exact same thing after solving. So, fun fact. Alright, but we do still have to consider that domain and range, and we really should change it to f inverse of x, because that's what they asked for. X plus 5 over 3. Alright, we run into the same problem here, that we have a radical. Radicals cannot be negative, so we want to figure out what would make that negative. X plus 5 over 3 has to be greater than or equal to 0. Multiply by 3 to both sides, you get x plus 5, and this actually stays 0 because 3 times 0 is 0. Then you subtract 5. Oh, x has to be greater than negative 5. Well, that makes sense. I mean, if we look at it, that makes sense, right? What would give us a 0 on the top, that when we divide by 3 we still get 0? Oh, it'd have to be whatever would be counter, the opposite of that 5, right? It would be negative 5. Okay, so x has to be greater than or equal to negative 5, or we're going to get a negative number. Okay, So that's our domain. As an interval, it would be -5 to infinity. Alright, now the range, that'll be so much easier, just gotta plug that in. What happens when you get a 0 there? You get a 0. Cool, it's gotta be square root of 0. So y, oh, pardon me. Let's try that again. So you would plug in y equals, and you get 0. So y is greater than or equal to 0. Y has to be positive. And that is true of this case because the whole thing is the radical, right? It's not a part of it like it was in the last problem. The whole thing is the radical, so the whole thing has to be greater than 0. All right. Let's try another one. Excuse me. All right, find the inverse of g inverse of the function g of x equals 7x minus x squared and determine the domain and range values over which the interval exists. Okay. Now I gotta be careful. Technically, we're supposed to put things in order of the exponent, right? So I'm gonna do a little rearranging. This is y instead of g of x equals y equals negative x squared plus 7x, right? You can see why someone would be tempted to switch that around because it's much prettier the other way. But this is truly what we have, right? This is truly what we have. So when we make that switch of values, oops, 7y, this is what we end up with, and we see that we have 2 occurrences of y, so we're going to have to solve it like we did the third example with the quadratic formula. Alright, and we're going to do that same little move, moving that over, right? We get 0 is equal to negative y squared plus 7y minus x. And now we see why it was so important to switch that and put it in order so that we could see that a is in fact -1, not b, so that we do this right. Alright, and then over here, y is equal to, let's see, what was it? B is 7, A is -1, and then of course C is -x, just like it was last time. So we have -7, oops, negative B plus or minus the square root of B squared minus 4, A, oops, -1. Oh, there we go. And then C is -x all over 2, which is A is -1. Okay, let's simplify this. That's equal to -7 plus or minus 49. Let's see, I have 3 negatives. 1, 2, 3, so it's going to stay minus 4x all over -2. I see a double negative here, -7, -2, so I'm just going to go ahead and erase those because that ends up being positive, and we have our function. This is our g inverse of x. Ta-da! Cool. I hope by now it's starting to kind of click that all you have to do is switch them, and then you're doing the exact same thing you've done for previous chapters, right? You just switch them and use what you know. Switch them, use what you know. Okay, but we do need to consider the domain and the range, which is the same problem as before. It's the same issue. Radicals can't be negative. So we're going to do the same thing. 49 minus 4x, that radicand, remember that means what's under the radical, has to be greater than 0. If it's not greater than 0, we have a problem. We have a big problem. So let's figure that out. So we get -4x. We subtract 49 to the other side because it's positive. Then when we divide by -4, we end up with positive, right? So we end up with x has to be greater than or equal to 49 over 4. Okay, that's a horrible fraction, but that's okay. So this is the domain. When we plug that back in, we know it's going to end up equaling 0, right? That's what we just solved for. If you don't believe me, then go ahead and plug 49 over 4 back into the radical, and you will see that you end up with 0. So for the range, we end up getting 7 plus or minus square root of 0 over 2. So y equals. So y has to be, sorry about that, y has to be greater than or equal to 7/2. That is the range. All right. It's not super complex so far, right? We just have to consider that domain and range. It may not be, you know, super straightforward, like times 2 by 6, but it's nothing we haven't seen before. The majority of the new stuff is just switching x and y, and that's how you find it algebraically. Just in case, let's do a rational, because why not? Rationals are fun. Find the inverse R inverse of x and the function R of x, for the function R of x equals 2 over x minus 1, and determine the domain and range over which the inverse exists. Well, we've seen that quadratics often yield radicals, right? And that makes sense. When you take a square and you inverse it, you get a radical. You get a square root, right? So what would be the inverse of a rational? Well, I don't know if you've ever seen one of these, but a rational equation, its graph kind of looks like this. You get two sides of it. Because of that fraction, it kind of creates a lot that doesn't exist. You get a really big asymptote. We're going to talk more about those the rest of the chapter. But you get a really big asymptote. When you inverse that, right, and you're sitting like this, you kind of end up getting the same deal. It depends on where the rational occurs, but you get another rational most of the time. Some of the times you get something even crazier, but here, and most of the time you get rationals back. No, I'm not going to ask you to graph a rational. Like I said before, for us the inverse is more about finding the algebra, not the graph of it. You could do it though. If you just take a table of values and you plot a bunch of points, you could connect them all and find the graph. You don't need anyone to show you how to graph any function if you make a table. It doesn't matter. You just need a table. But like I said, for this chapter, we will not be graphing rationals. So let's just try taking it using the same set of rules we did before. So R of x, I'm going to go ahead and change that to y. So y equals 2 over x minus 1. Right? Not the most complex rational we've seen. Definitely not even close, right? It's just a rational because it's a fraction. But let's go ahead and switch those. We end up with x equals 2 over y minus 1. We'll switch a Rooney. And now we have to solve. Don't panic, it's a rational, but it's not that complicated. This is a nice easy one because we don't have any other rationals. We don't have to add, find LCDs, we'll do one of those later. But here I just have to switch. So I have my variable I'm solving for in the denominator, and that's the first problem I want to take care of. So I'm going to multiply it up there. Y minus 1 times x equals 2. And then I'm going to move that down there. So y minus 1 equals 2 over x. And that's much easier to work with. Right now the x is out of the way. My y is almost by itself. Just have to add 1. So 2 over x plus 1. And indeed we did get another rational. Right? We got 2 over x, which is a rational. And then we're going to add 1 to it. Okay. So this is R inverse of x equals 2 over x plus 1. Remember, don't forget to use the inverse notation to tell the audience that yes, this is in fact the inverse of this function, or vice versa. Let's consider the domain and range now. Domain is actually pretty easy here. What's the one thing that would make this fall apart? It has nothing to do with the radical now. Having a 0 in the denominator would be a problem, right? That's usually the problem with a rational. Remember all those extraneous solutions and whatnot? That's what we're hunting for again. So what would be the problem here? X cannot be 0. So one way to write this is x cannot be 0. It's not that x has to be greater than 0, right? You can have a negative down there. You could have 2 over negative 2. You could have 2 over negative 8. It would simplify, right, to just a negative number. So x cannot equal 0. The interval of that would be from negative infinity to 0 and then not including it. That's all the negatives. Union 0 to infinity, okay? So it's kind of a double interval here. You've got the negative half on the left, negative infinity to 0, parenthesis, because you don't want to include it, and that's what the U in the middle means, union, like union together, like when you get married, you and your husband, right? And then on the top we have not including 0, so hence parenthesis to infinity. So negative infinity, 0, parenthesis, union, parenthesis, 0, infinity. Okay, cool. I have no problem with this, but your homework would like that. Okay, so take a note. And then the range, once again, you just plug it in. It's kind of hard to see what isn't allowed here, right? Because you can't plug in 0, right? You can't plug in like has to be greater than 0 or has to be, it's complex. So we don't want to use this format. If though we take a look, let's look up here, because that's the same equation, right? It's the same thing, just rearranged. It's rearranged. I put it back into its original form. What can't y be? What is y never going to be? Yeah, it's never going to be 1. So it's the same kind of deal here. Y cannot equal 1. And we draw the same kind of weird double interval. So y can't, negative infinity to 1, union 1 to infinity. And y can't be 1 because of this, right? That would technically yield the same, like, oh, if you did that, you would get 0 on the bottom, and that's what 2 minus, yeah, it just wouldn't work, right? Because everything would explode about it. There'd be a problem. So that's the domain and range. All right. Man, I managed to fit all that in a very short part. Okay, example number 7. Below is the function f of x equals 2x minus 3 minus 1 and its inverse g of x. Write an equation for the possible inverse of g of x using algebraic methods. Whoops. Then verify your written equation using points from the graph of f of x and g of x. Okay, well, let's just take 1 point from f of x first. I'm just going to borrow some of this space up here. And then we will worry about finding its inverse. Let's make sure, in fact, that what we see right here is f of x. So let's look at this. I think a good point to choose, let's choose this one right here. So that's the point out 1, down 1, 2, 3. So this is the point 1, comma 3, negative 3, pardon me. Out 1, down 3. What does it mean to check a point? Well, remember that any equation, when you plug it in, it's supposed to give you the point as a solution, right? So if I were to take 1, plug it into this equation, I'm supposed to get negative 3. That's what's supposed to happen. That's how that line got drawn, right? We're going to use that fact a lot later on, so it's very important to remember that. If you have an equation and you plug in the x, you should get the y. That's what's happening. So let's try that out. Let's plug in 1, excuse me, and make sure we get negative 3. So 1 squared minus 3 times 1 minus 1. Notice every occurrence of x became 1, right? All right, so we get 1 minus 3 minus 1. Well, 1 minus 1, or we could go in order. That's negative 2, minus 1, negative 3. Okay, check. So this is actually the graph of f of x, right? Now we could say, well, you gotta check more than one, and that's fine, but we don't have time for that right now. So we're gonna assume that seemed to work. All right, let's find the inverse now. This is a picture of it, but let's do it algebraically so we don't go mad trying to find all those points, right? So we're gonna say y is equal to x cubed minus 3x minus 1. Cool. And then we flip-flop. X is equal to y squared minus 3y minus 1. Every occurrence of x became y, every occurrence of y became x, right? Just switch it around. Okay. From here, I know it's super, super tempting to say you want to just plug that into the quadratic formula, but remember, it doesn't equal 0 yet. It doesn't equal 0 yet. We saw this a lot in the word problems, right, where there's always that, you know, if it's up 115 feet in the air and you actually have to move the 115 over before you're allowed to do anything. Same thing here. It's just this time it's an x you have to move over. But it's the same cheater move. So I end up with 0 equals y squared minus 3y minus 1 minus x. It is not minus 1x or positive x. Okay, you're not multiplying, you're still just subtracting. The only thing is maybe you want to put some kind of mini parenthesis around that to remind yourself that this is in fact the whole c term. Okay, so this expression is c. We haven't done that before, but it's not a big deal, right? It's the whole thing is now c. I've got a equal to 1, I've got b equal to negative 3, and I've got c is negative 1 minus x. Okay, so quadratic formula time. x is equal to minus b plus or minus square root of b squared minus 4, a is 1, and c is now this whole little mini expression all over 2 times a. Alright, little simplification, you get 3 plus or minus square root of 9. Alright, I gotta be careful now. So negative 4 times 1, that's just going to be negative 4, right? So now I have to worry about distributing that in. That negative 4 is going to both of them. So it's going to be plus 4 plus 4x, right? Negative 4 times negative 1 gives me the 4. Negative 4 times the negative x gives me the 4x. All over 2. Last little thing I can do is maybe make this 13. 9 plus 4 is 13. And I think that's it. That's about it. This is now g of x is what they wanted to call it here instead of f inverse of x, but it's g of x. And that's it. Awesome. Let's double check that this is in fact the same g of x we see on the page. So let's pick a point. We kind of picked one over here. Let's pick the same one. Let's pick one over here. Interesting. This is back 1, 2, 3, and up 2. So back 3 and up 2. Back 3 and up 2. So this is 3, comma 2. Negative 3, comma 2. What are we supposed to do with this? What was this supposed to be done with? How do you check a point? Oh yeah. Okay, so we're supposed to plug in negative 3 and hope we get 2, right? Cross our fingers to hope we get 2. So we plug that in, g of negative 3, right? It was back negative 3. Back 1, 2, 3. Good. That's really interesting. And now we change all the x's to negative 3. Okay, solving that a little bit, because that so far doesn't look like 2. We get 3 plus or minus, let's see, 13 minus, what's that? 12 minus 12, that's 1 over 2. Square root of 1 is 1. Alright, so plus 1 here, if you recall from chapter 9, this is where you have to kind of break them off. We get 4 halves or 2 halves. We get 2 or 1. Very nice. So we do in fact get 2. And we also got 1, right? We also got negative 3, 1. If we check that, we go back 1, 2, 3, and up 1. That is also a point on this graph. That's cool. What's cool about that one is let's compare that to the point we chose to begin with. 1, negative 3. Notice it's backwards, right? That was actually the inverted point. That was the inverse flip over. That's where it is. And I know that because x and y have been switched. Remember, at the end of the day, that's what these are. There's flips over the lines, y equals x. Y equals x. Cool, and we proved it. Did they ask us to find the domain and range here? They did not, so we do not have to. Okay, we've got 2 more today. We are going to... no, 3 more today. 3 more today. If you, like I said, if this is an absent video, please watch the whole thing. If you're just using this as a supplement and it makes sense now, you can go back to your homework. If you still have questions, though, please come see me. That way we can work through where you're kind of missing stuff. But going on to example 8, which of the following are inverses? Let's try this one. So we have 6 functions here, right? The easiest way to see if they are inverses is to, in fact, invert them. So they are, hopefully, inverses of each other. Let's see what we have. So f of x, let's find f inverse of x. Well, in order to do that, I'm going to change it to y equals 8x cubed. This one's a cubic. I wonder what that's going to be inverted. It could be interesting. Let's change x and y. Same process. Same exact process as before. Switch those around. And now solve. So divide by 8. You get x over 8 equals y cubed. How do you get rid of a cube? You cube root it. So we end up with cubed root x over 8 equals y. A little simplification. My apologies for the tiltedness of this. Cubed root of 8 is 2. So I have the cubed root of 8 over 2 equals y. And so we get the cubed root of x over 2. Do we have that anywhere? We do. So it looks like these two are inverses. Looks like A and E are inverses. Sweet. 2 down, possibly 4 to go. Alright, we have the square root of x plus 3. So I'm going to change that to y. And then I'm going to invert. Right? Invert. And then I'm going to solve it. So now, how do you get rid of a square root? Interesting. We've been given a lot of squares today. We haven't been given a lot of square roots, but it's the same process. Just square it. Right? It's the same duo, the same two. So we end up with x squared equals y plus 3. And now we get y by itself by doing x squared minus 3 equals y. So it looks like G inverse, totally bleeding into the next problem, that's okay. G inverse is equal to x squared minus 3. Do we have that anywhere? Nope, doesn't look like it. That's okay. That's alright. We'll just have to do 4 more, or 3 more. Alright, let's try this one out. So we have, this is y equal to 3x over x plus 3. Switch them. You get x is equal to 3y over y plus 3. Okay, irrational. We can handle that. Remember, when you're solving for a rational, you want to put the variable in question at least in the numerator. That's the first thing you want. You want to get rid of it in the denominator. So I'm going to move that up there. Y plus 3 times x equals 3y. It is not y plus 3 equals 3y, right? We're not solving for y. That x is still there, it's just on the other side now. But now it's on the bottom. No, I don't want to do that. I would want to do that if it was like a 3 on the top, not a 3y. If it's a 3 on the top, then I've got y all by itself. Cool. But if I put the x on the bottom, I've got the same problem that I have right now, where x and y are together. So I don't want to do that. Instead, I got to get rid of all the parentheses. I got to get rid of these parentheses. So I'm going to distribute that x in. I get yx plus 3x equals 3y. And now I'm going to put all the y's on both sides, on the same side again. You're like, Miss K, what are you doing? I am trying to get 2 y's into 1 y. Okay, whoops, that should be a minus sign, right? Because we've minused it to the other side. I'm trying to get 2 y's into 1 y, and the only way I can do that is to factor it out. So I first have to split it up, and then I got to factor it out. Now I have 1y. So you see how I did that there? Let's go back and review that for a sec. So what I did was I moved it out of the denominator, right? Starting back up here. We moved it out of the denominator. Then I moved the x in so there would be no parentheses. Then I put all of the y's onto one side. Why did I do that? Is so I could take them both out and make them 1. I can't do that until the expression of y plus 3 becomes 2 different things. So once it's 2 different things, I can take out the part that is y, right? So I can't take it out if it's still attached to the plus 3, but if I get it away from the plus 3, then I can actually put it back with all the y's and take it out as a factor, okay? Alright, okay, so now I've got one occurrence of y, just divide by everything that isn't y, and we get that y equals 3x over 3 minus x. No, we don't. Yes, we do. Alright, and that, what letter is this? Is H inverse. So H inverse is 3x over x minus 3. Do we have that anywhere? We do. It's the same thing as J. Fabulous. Okay, so we use this one. That was an inverse. What is the inverse of this one? It looks very close to this. It could even be a Miss K typo. It's probably a Miss K typo. And yours, you might be scratching your head because those are actually the same. I do plan on changing that. But for right now, they're not the same. right? Those are very much not the same, and you have to be careful of that. Its order is very important if you're playing a matching game, right? X cubed is not x squared. So what would be the inverse of this one? What would it look like? Well, it's a cubic, so it's probably going to be a cubed root. But let's try it out. We get y equals x cubed minus 2. We don't have a whole bunch of other x. Oh, sorry. We have to switch the variables. Slow down, Ms. K. Gotta switch those variables. So switch the variables. But now we don't have a lot of occurrences of y, just the cube, right? If it's all by itself, it's super easy. It's when you get 2 or 3 or 4 different y's that have terms in it that you can't combine that becomes complicated. Here, though, it's only the 1. So we'll just add to the other side. We get x plus 2 equals y cubed. Cube root both sides. We end up with cubed root of x plus 2 equals y. That would be our inverse, right? And we could really just change this to m inverse of x. That would be our inverse. So that is not quite the same as what we had up here, the square root of x plus 3, right? Now we don't need a plus or minus because it's a cube root. Okay. Last thing we're going to do in this section is 2 real-life examples, right? We want to do some real-life examples, kind of relate this, like what the heck are you talking about? And we really do want to tackle one of those harder rationals. So let's read this one together. An automobile manufacturing plant takes one model of robotic welder T seconds to wield a car chase frame. The time it takes the second model to weld the frame is T minus 1 seconds. The function that describes how long it takes the 2 welders to work together to weld the frame is 1 over WT is 1 over T plus 1 over T minus 1. Find the inverse of the function and describe the restricted domain over which it is defined. We've seen this before. This is just a work rate problem, right? It's just a work rate problem. We need the inverse of it now, right? The work rate is a great example of an inverse. Great example. The time it takes you to do a job, the inverse of that, right, 1 over that, is going to be, the reciprocal of that is going to be your work rate. So naturally, the inverse should be something we definitely want to find. Okay. The function itself is w of t, right? So we're going to write w of t. I'm just going to write w because I don't want to write of t over and over again. But that is what we are calling the function. So 1 over w equals 1 over t plus 1 over t minus 1. Before we were switching x and y. Now we're switching w and t. So let's go ahead and switch that. 1 over t equals 1 over w plus 1 over w minus 1. That's not super complicated. Just switching letters, right? Just switch the letters. So this is now the inverse of the work function, right? It is irrational. It does have unlike LCDs, so we're going to have to do some maneuvering. But I'm just going to multiply everything by least common denominator, okay? Least common denominator here would be t, w, and w minus 1. Cool. What's missing from the first one? W and w minus 1. What's missing from the second one? T and w minus 1. What's missing from the third one? T and w. Okay, I'm done. If you have no idea what I just did, then you should go back to chapter 7 and review 7.4, 7.5, around there, how to solve rational equations. Okay, what we did was we multiplied each one of these fractions by that whole combination of LCD, and whichever one was there got canceled. So whichever one was already, or whichever ones were not there, those are what was left behind. So for example, in 1 over t, when I multiply that by t, w minus 1, the t's cancel, and I'm left with w and w minus 1. So what you're left with is all on the top is always the 2 that are not there, and the denominator actually goes away. It's what we call clearing the fractions. Okay, so if that was just way over your head and you're like, whoa, I totally forgot that, or for some reason I wasn't here, I have no idea what you're talking about, go back to chapter 7, review that, or come see me, and we will do a few together, okay? Alright, but from here, I'm going to get rid of those parentheses. I have w squared minus w equals tw minus w plus, minus t plus tw. Okay, cool. Once again, I'm solving for W. Remember that, I'm solving for W. W is the function, so I want W. But I see a quadratic, W squared, and I see a lot of singleton W's, so we're going to have to use quadratic formula. I'm going to put everything over there. 0 equals negative W squared minus W, right? Because it was, oh, it's minus to begin with, so plus W. So I move those two over. Just move those two over to the other side. And everything else just stayed the same. TW, let's do that, minus T. I'm not combining anything right now because I want you to just see that all I did was move those two over. Okay, now I'll combine stuff. We end up with 0 equals negative W squared plus, let's look at all the W things. We have 1 T and T, so 2 T's and 1 of the W's, and then minus T. That's what we have. Alright, cool. So that's everything. Alright, I know it doesn't look quite like it, but we do in fact have a quadratic formula. A is negative 1. B is this whole 2t plus 1 expression, and C is negative t. So there's a lot more variables than we've seen before, but that's okay. The quadratic formula works no matter what. So W equals minus B 2t plus 1 plus or minus the square root of 2t plus 1 b squared minus 4. A is negative 1. C is negative t. All over 2 times A is negative 1. Alright. I am seeing two negatives here, so those are going to cancel, and I'm just left with 2t plus 1. Plus or minus. Now remember, 2t plus 1 squared is not 4t squared plus 1. It's close, but there's going to be a middle term. So over here on the side, we'll even do it up here, we're going to do 2t plus 1 times itself, because that's what 2t squared plus 1 squared means, right? That's what it means when you square something times itself. So we end up with 4t squared plus 2t plus 2t plus 2. Okay, so 4t squared plus 4t plus 2. 4t, I'm saying t a lot, plus 4t plus 2, and then this would be negative, 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 minus 4t. All over 2, right? Because we got rid of the negative with the negative on the top. Alright, super close. These two are going to cancel, right? 4t and negative t. We end up with 2t plus 1 plus or minus the square root of 4t squared plus 2. All over 2. We could factor out a 2, but that wouldn't help us too much. So we are finished. There's not much more we can do under that radical, those t squareds. If it was a minus, I might consider some difference of squares, but there's a 2 there, so it wouldn't even be. Since it's a plus, we are done. This is the function W inverse of t. Woohoo! Now, if it would make more sense to you to convert that to x and y and then change it back, that's totally fine, but you do need to convert it back. Last but not least, we want to determine the domain, right? They asked us about the domain, and it's restricted. That's an interesting thought, right? Restricted domain. Let's just do this like it was a regular old problem, right? Like it was just something that we did before. We'd look at it and say, you know what? That can't be a radical. The t in front, that's okay, right? We can have a 0 there, a negative number. It just might be negative, right? And maybe that doesn't, well, that doesn't break any laws. But the radical, that can't be negative. So what would that be? What would make that negative? So we have 4t squared plus 2 has to be greater than or equal to 0. Luckily, we don't have another t there, right? Luckily, our 4t and our 4t canceled each other out. Or 4t and our negative 4t canceled each other out. So we now have just a nice, easy thing to solve. So we'll subtract 2. Greater than or equal to negative 2. T squared greater than or equal to 1/2. t is greater than or equal to plus or minus the square root of 1/2. All right, so t has to be greater than or equal to plus or minus the square root of 1/2. What the heck does that mean, right? What the heck does that mean? That means it has to be greater than or equal to both positive square root of 1/2 and negative square root of 1/2. Well, if you're going to be greater than negative, you're going to be greater than the positive, right? Or sorry, if you're going to be greater than the positive, you're going to be greater than the negative. So this part is unnecessary, right? Because we're already bigger. What is the square root of 1/2? Let me find that fraction. I don't often find this. Okay, square root of 1/2 is 0.7071076. So we're about at 0.71, right? If you're already bigger than 0.71, you're going to be bigger than negative 0.71. So this part is unnecessary, right? Okay, cool. But let's think about the context of the problem, too. What does t have to be greater than? Can t be negative? Why are we using t instead of just x and y? Because t now represents something. T represents a time, a number of seconds. So t couldn't even be negative to begin with, right? Work rate couldn't be negative to begin with, right? It's got to be greater than whatever we get when we plug in t, right? So we plug in, it doesn't ask us to do that, but that's basically the same thing. You have to think about the context of the problem. Luckily, our work already kind of did that for us. Sometimes it doesn't, though. Sometimes we would get something like t has to be greater than -5, and we'd say, actually, t has to be greater than 0, because it doesn't make sense in the problem to have -2 seconds, even though that works in the function. We come back to that, well, does it fit the model, right? Does it fit the modeling that we're trying to use this math equation for? Okay, one more, and then we're done. I know it's been kind of a long section. There's a lot with inverses. The key ideas are about switching, but we'll do one more and we'll call it done. The amount of variation in the pressure of natural gas pipeline that a natural gas pipeline can stand without triggering an alarm at the closest monitoring station is given by the absolute function f of x equals x minus 25, where x is greater than 0. The alarm, and I do apologize, that is a typo. For some reason the thing didn't print. It should be the absolute value of x minus 25, where x is greater than 0. The alarm is triggered if the pressure variation function rises above 40 units. Write the inverse of this function and describe the restricted domain of the inverse and the function itself. So now they want both, the one for the domain and they want the domain for the inverse and the domain for the function. Okay, let's just start with the domain for the function. It's right there. Let's just think about it. Why do they put x is greater than 0? Why? Why would they even bother with that? This is the domain. The domain is that x is greater than 0. I'm going to write that smaller. The domain is the fact that x has to be greater than or equal to 0. Why? Because x has to be x is the units, right? X is the units of gas in the pipeline, right? It's the gas in the pipeline that triggers the pressure. The function is the pressure. So if the x is the units, can you have negative units? No, that doesn't make any sense, right? So it's going to be the units. And that makes sense that it's greater than 0. All right, let's find the inverse now. So we have y equals the absolute value of x minus 25. Now we have not dealt a lot with absolute value. Okay, and I'm probably not going to ask you one of these on a test or even on a homework, but you should see it. You should see one of these, okay? You should see the absolute value. Switch it out. Why should you see this? Because it has nothing different. It has nothing different than any other inverse. It's just switch it out. Just switch it out. That's all. The only thing now is to solve an absolute value, you have to consider it in two domains. The absolute value doesn't have anything on the outside, so we don't have to worry about that. But you're going to have one case where it equals positive y minus 25, or one case where it equals negative of the whole thing. Okay? So absolute value functions, if you're wondering why, they kind of look like this. They bounce always positive, right? Always positive. So like the straight y equals absolute value of x looks like this. That's the parent function. We'll talk about that later. It bounces. So you've got the two sides. It's what we call piecewise function, right? You got two sides of it. So because of that, we have to solve both. Now in this case, we may be able to wrap it back together. We don't know yet. Back together into one function. But we want to see what the inverse will be. So let's try it out. So move this one. We get, add 25 to the other side, y equals x plus 25. Or, we do it over here. Move that in, you get x equals negative y plus 25. Subtract that over, you get x minus 25 equals negative y. Right? Just move 25. Now you multiply everything by negative 1. Y equals negative x plus 25. Bummer. These are not exactly the same equation, nor are they exactly opposite. So it's going to stay piecewise. Right? If it was negative x minus 25, then we can say it was the absolute value of x plus 25. Don't worry about that. But it is piecewise. It's 2. So, and we end up getting something like that as our absolute value, as our inverse function, right? Because it's over the y equals x. Okay, so we found the function. Let's think about the domain now of each of these. What's the domain? Do you see anything that would be a problem plugging in this function? No, the domain could be anything, right? But once again, what is x? If x has to start greater than 0, yeah, it's got to also be greater than 0 in the inverse as well. So when it comes to the function, no, anything you can plug in anything you want. You can plug in a fraction, you can plug in a negative number, you can plug in a positive number, right? It wouldn't matter. But x has got to be greater than 0 in the context of the problem. In fact, no matter what number you plug in, you're going to get a y value that's positive, right? You're going to get a y value that's positive. But the domain of the function, because it's in units, because we're talking units of gas, you can't take away the gas out of the air, right? I mean, you could, but it's not going to be negative, right? You're not going to have negative particles of gas in the air. So the domain for both has to be x greater than 0. All right, that is inverses. Like I said, absolute value will not be in the cube, but you have to know about linears, quadratics, radicals, rationals, all the stuff we've talked about this year is up for grabs, okay? So cubics, those are in there too. Fifth powers, all polynomials, but you can do it. You can do it. It's all about flipping over that line y equals x, right? When you do that, you switch the x and the y. That's all that happens. You just switch the x and the y. That's inverses. We're going to talk about 2 certain inverses next time, and that's going to be the main focus of the chapter. But if you have any questions, let me know, and I'll see you later.